We've all heard the story. The universe began with a bang, an unimaginably powerful explosion that sent matter and energy hurtling through the void, creating everything we see today. But surely that wasn't the true beginning. Something could not come from nothing, right? What existed before the Big Bang? This question goes beyond what we can observe. And yet it's the one that holds the key to understanding the very nature of existence, the origins of cosmological curiosity. As long as people have existed, they have looked up at the sky and wondered how it all began. Early humans used the stars and the patterns in the sky to navigate and mark the passage of time. These observations naturally led to questions about the universe's origins, and these questions began to shape how different cultures viewed the world and their place in it. In ancient times, many civilizations developed stories to explain the creation of the universe. These stories, now known as creation myths, were attempts to grapple with the big questions. What existed before the world? Who or what created it? How did it all come together? For many ancient people, the answers to these questions were tied to their gods and spiritual beliefs. The ancient Sumerians, one of the first known civilizations, imagined that the universe began with a vast chaotic sea. From this chaos, the gods emerged and shaped the world. In Egypt, the creation stories centered around the god Atum, who rose from the waters of chaos to create everything. Similarly, in ancient Mesopotamia, the Babylonian creation myth, called the Enuma Elish, described how the god Marduk defeated a great sea serpent and used its body to form the heavens and the earth. In ancient Greece, the earliest philosophers tried to understand the universe without relying entirely on myths. Thinkers like Thales, Anaximander, and Pythagoras began to ask whether the cosmos could be explained in natural terms. These early Greek philosophers sought to find the fundamental substances or principles that made up the universe. They believed that understanding the cosmos could reveal truths about its beginnings and how everything fit together. Even though they moved away from mythological explanations, their ideas were still deeply rooted in a sense of wonder about the universe's origins. The Mayans of Central America developed a detailed cosmology based on their observations of the stars. Their calendar systems and astronomical knowledge were closely tied to their beliefs about the creation of the world and the cycles of time. As humans continued to observe the world around them, these early ideas about the universe's origins would evolve, laying the foundation for later scientific thought. But in the beginning, it was the wonder and curiosity about the stars and the sky that led ancient civilizations to ask questions about where it all began. What is nothing really? Philosophical and scientific perspectives. As our knowledge of the cosmos has grown, we've discovered much, but also learned that some ideas only display their complexity once you dig beneath the surface. Take the idea of nothing, which has puzzled humans for centuries. It seems like a simple concept at first. Nothing is the absence of anything, a complete void. But when we try to understand it more deeply, it becomes tricky. Is it possible for there to be true nothingness anywhere in the universe? It's a pertinent question if we wish to answer whether or not our universe started from nothing. Both philosophers and scientists have tried to answer this question, and their views have evolved over time. Even as far back as ancient Greece, some philosophers believed that the idea of nothing was impossible. The philosopher Parmenides argued that something could never come from nothing. To him, the universe had always existed in some form. He believed that if there had once been nothing, then there would still be nothing, because you can't create something out of nothing. This led to the idea that the universe must be eternal and unchanging, always filled with some kind of substance. Other philosophers, however, took a different view. The idea of a vacuum, or an empty space where nothing exists, was first proposed by ancient thinkers like Democritus. He believed that the universe was made up of small, indivisible particles called atoms moving through empty space. This concept of the vacuum suggested that nothing could exist, but it was just the absence of matter, not an absolute nothingness. As our understanding of the universe grew, the concept of nothingness became more complicated. In the field of physics, the vacuum of space once seemed like a perfect example of nothing. Outer space, with its vast emptiness between stars and planets, appeared to be a place where nothing existed. For a long time, scientists believed that the vacuum of space was completely empty, without matter or energy. But modern physics has shown that even in the vacuum of space, there is never truly nothing. Even in the emptiest regions of space, there are tiny particles that pop in and out of existence, a phenomenon known as quantum fluctuations. These particles appear for just a fraction of a second before disappearing again. This means that even the vacuum of space is not completely empty. It is filled with these fleeting particles, as well as fields of energy that are constantly shifting and changing. This discovery changed the way scientists think about nothingness. In quantum physics, the vacuum is not a simple empty void. It is a place where strange things happen at the smallest scales, a sea of energy and particles that behave in ways that are difficult to understand. Some scientists even think that these fluctuations in the vacuum might have played a role in the formation of the universe itself, creating the conditions for the Big Bang. Philosophers have also reconsidered their ideas about nothingness. Some argue that true nothingness might be impossible because our minds can't fully grasp the idea of complete absence. Whenever we think of nothing, we still imagine a kind of empty space, but space itself is something. This has led to debates about whether it is even meaningful to talk about true nothingness, or whether it is just a concept that humans invented. So, does true nothingness exist? To answer this question, we need to dive deeper into this topic. The Big Bang, a gateway, not a beginning. We need to take a look at what seems to be the true beginning of everything, the Big Bang. According to the Big Bang theory, the universe started as a tiny, incredibly dense point, often called a singularity. Around 13.8 billion years ago, this point rapidly expanded, and from that expansion, everything we see today, stars, planets, galaxies, was created. However, some scientists and thinkers are beginning to rethink this idea. Instead of viewing the Big Bang as the absolute beginning of everything, they see it as a gateway, a threshold marking a change from one state to another. In this view, the Big Bang wasn't the start of the universe, but rather a transformation of something that already existed. One reason for this shift in thinking is that the Big Bang theory doesn't explain everything. It describes what happened after the universe started expanding, but it doesn't answer the question of what caused the singularity or what existed before the Big Bang. When scientists look back to the very first moments of the universe, they reach a point where our current understanding of physics breaks down. There are several ideas about what might have come before the Big Bang. One of these is the idea of a cyclical universe. In this model, the universe goes through cycles of expansion and contraction. The Big Bang could be seen as the result of a previous universe collapsing in on itself, creating the conditions for a new one to form. After a long period of contraction, the universe would reach a point of extreme density, similar to the singularity described by the Big Bang theory. Then, instead of continuing to shrink, it would expand again, leading to the universe we see today. This would mean that the Big Bang wasn't the beginning, but just part of an ongoing cycle that has been happening for an unimaginable amount of time. Another idea is that our universe is just one of many. In the multiverse theory, there are countless other universes, each with its own set of physical laws. Some of these universes might have started with their own Big Bangs, while others might exist in completely different ways. In this view, the Big Bang could be the beginning of our universe, but not of everything that exists. The multiverse itself might have no beginning or end, with new universes constantly being born. There's also the possibility that what we call the Big Bang was actually a transition between different phases of the universe. Some scientists suggest that before the Big Bang, the universe might have been in a different state altogether. One idea, known as the Big Bounce theory, suggests that the universe could have been in a state of contraction, slowly collapsing in on itself. Then, at a certain point, it bounced and began expanding again. leading to the universe we observe today. In this case, the Big Bang would be the point where the contraction stopped and the expansion started, but not the beginning of time or existence itself. These new ways of thinking about the Big Bang don't mean that the theory is wrong. The evidence for a rapid expansion of the universe around 13.8 billion years ago is strong, and all of the data agrees that something like the Big Bang did happen. But the question of what came before, or if there even was a before, remains open. As our understanding of physics continues to grow, we may find new clues that help us answer these deep questions. Let us explore what some of those possibilities might be through the lens of various theories. Tunneling from nothingness, quantum origins. Many of the most fascinating ideas arise from the strange world of quantum mechanics, where the rules of nature are very different from what we experience in our everyday lives. Quantum tunneling is a phenomenon where particles can pass through barriers that would normally be impossible to cross. In classical physics, if you imagine rolling a ball up a hill, it will only reach the top if it has enough energy. If it doesn't, the ball will roll back down. But in quantum mechanics, particles don't behave like solid objects. Instead, they exist as waves, with probabilities that allow them to tunnel through barriers they wouldn't normally be able to cross. This means that, on very small scales, particles can suddenly appear on the other side of a barrier, even if they didn't have the energy to get there by normal means. When applied to the origins of the universe, the idea of quantum tunneling suggests that the universe could have tunneled into existence from a state of nothingness. In this context, nothingness wouldn't mean a complete absence of everything, but rather a quantum vacuum, a state where there is no matter or energy as we understand it, but still a possibility for fluctuations and particles to emerge. This is sometimes called the quantum vacuum, or false vacuum. Even though it seems empty, this vacuum can still give rise to quantum events. In the early 1980s, physicists like Alexander Vilenkin developed models that showed how the universe might have arisen through quantum tunneling. According to this idea, the universe started as a small bubble in the quantum vacuum. Through quantum fluctuations, this bubble could have tunneled into a state of rapid expansion, leading to what we now call the Big Bang. In this way, the universe could have emerged from a kind of quantum void without needing any pre-existing material or energy. One of the key ideas behind this theory is that in the quantum world, the concept of nothing is very different from what we usually think of. Even in the absence of matter, energy, and space, there is still a kind of background structure, fields, and potential energies that can give rise to something. This is why quantum tunneling can occur even in what seems to be empty space. The idea that something can come from what looks like nothing is a central part of quantum theory and is supported by experiments that show particles appearing out of the vacuum for brief moments. This idea challenges the traditional view of the Big Bang as a singular point where everything began. Instead of requiring a singularity with infinite density, the quantum tunneling model suggests that the universe could have come from a small, stable region of space that suddenly expanded. This avoids some of the problems associated with the singularity, such as the breakdown of physical laws at infinite densities. There are still many questions about how this process might have worked. One challenge is understanding the exact nature of the quantum vacuum that could have given rise to the universe. The vacuum in quantum mechanics is not a complete void, but it's still unclear exactly what properties this nothingness would have had before the universe came into being. Another question is whether the laws of physics themselves might have arisen from this process. If the universe emerged through quantum tunneling, it raises the question of where the laws that govern quantum mechanics came from in the first place. Inflationary theory, a runaway expansion before time. Another theory is one of cosmic inflation. According to this idea, just after the Big Bang, the universe went through a period of incredibly fast expansion, much faster than the rate of expansion we see today. This period of rapid growth is called inflation, and it lasted for a tiny fraction of a second. Even though inflation ended very quickly, it had a huge impact on the universe we observe now. Before the theory of inflation, there were certain puzzles that the traditional Big Bang theory couldn't solve. One of these is known as the horizon problem. When we look at different parts of the universe, they all appear to have nearly the same temperature. But if the universe had expanded at a steady rate since the Big Bang, these regions wouldn't have had enough time to come into contact with each other and exchange heat, which would make their temperatures equal. Inflation solves this problem by suggesting that, before the rapid expansion, the universe was much smaller, allowing different regions to even out their temperatures before inflation stretched them far apart. Another puzzle is the flatness problem. In cosmology, flatness refers to the geometry of the universe. If the universe were too curved, either it would have collapsed back in on itself, or it would have expanded so fast that galaxies wouldn't have been able to form. But observations show that the universe is almost perfectly flat. This is strange because in the early universe, it seems unlikely that it would be so precisely balanced. The theory of inflation explains this by stretching the universe so much that any initial curvature would be smoothed out, making the universe appear flat, much like how the surface of a balloon becomes smoother as it is blown up. The term cosmic inflation was first coined by physicist Alan Guth in the 1980s. Guth realized that inflation could not only solve the horizon and flatness problems, but also explain why the universe is so large. Inflation describes a universe that starts off very small, perhaps smaller than a proton, and expands rapidly, doubling in size over and over again in an incredibly short time. This runaway expansion made the universe enormous in a fraction of a second. While the inflationary theory explains many features of the universe, it also raises new questions, especially about what might have happened before inflation began. In the traditional Big Bang model, the universe starts with a singularity, a point of infinite density and temperature, and then begins to expand. But inflation suggests that something might have existed before the Big Bang, something that triggered the inflationary period. In this view, the Big Bang could be seen as the end of inflation rather than the beginning of everything. One idea is that inflation could have been driven by a mysterious form of energy known as the inflaton field. This field is different from the kinds of energy we observe in the universe today, like electromagnetic energy or gravitational energy. Instead, the inflaton field is thought to have filled the early universe and caused it to expand at an exponential rate. As inflation progressed, the inflaton field lost its energy, which was then converted into the particles and radiation that make up the universe as we know it. In this model, the universe didn't start from a singularity, but from the inflaton field gradually releasing its energy and transforming into matter. Another possibility is that inflation could be eternal. This concept, called eternal inflation, suggests that inflation didn't just happen once, but is still happening in other parts of the universe, or more accurately, in a multiverse. According to this theory, our universe is just one bubble that stopped inflating, while other regions of space continue to expand at an accelerated rate. New bubbles are constantly being formed as inflation continues elsewhere, each potentially creating a new universe with its own set of physical laws. In this model, inflation never truly ends, and the Big Bang was just the moment when our particular bubble stopped inflating and became the universe we observe today. This idea that inflation could have pre-Big Bang implications is currently under exploration, with scientists working to find evidence that could support or challenge these ideas. One area of focus is the cosmic microwave background, CMB, the faint afterglow of the Big Bang. By studying small variations in the CMB, scientists hope to learn more about the conditions of the early universe and possibly find clues about inflation. Some researchers are also exploring whether gravitational waves, ripples in the fabric of space-time, might provide evidence of inflationary processes. These waves could carry information about what happened in the first moments of the universe, or even before. Quantum fluctuations, the seeds of a universe? Returning to the realm of quantum mechanics, there is the idea of quantum fluctuations, which are tiny, unpredictable changes that occur in the fabric of space itself. They are in fact one of the most fundamental aspects of quantum mechanics. Even in what seems like empty space, these fluctuations constantly happen, creating brief, random changes in energy. This activity occurs everywhere, even in a perfect vacuum where no matter or energy appears to exist. It is a reminder that, in the quantum world, nothing is never truly empty. In the context of cosmology, these quantum fluctuations may have played a crucial role in the formation of our universe. The idea is that small, random disturbances at the quantum level could have grown into the large structures we see in the universe today, such as galaxies and clusters of galaxies. But how do tiny, microscopic fluctuations lead to something as vast and complex as a universe? The key lies in inflation, once again. During this inflationary period, quantum fluctuations were stretched to cosmic scales. Before inflation, the universe was a tiny, nearly uniform region, but it was filled with constant small quantum disturbances. As the universe expanded at an extraordinary rate, these tiny fluctuations were stretched out, becoming much larger than they originally were. What started as a microscopic instability in the quantum world became a large-scale feature of the universe. These stretched-out fluctuations created small differences in density across the early universe. Some areas had slightly more matter, while others had slightly less. Over time, these small differences grew. Regions with more matter attracted even more matter through gravity, forming the seeds of stars, galaxies, and other large cosmic structures. In this way, quantum fluctuations became the seeds of the universe's large-scale structure. One of the strongest pieces of evidence for this process comes from observations of the cosmic microwave background, or CMB, the faint glow of radiation left over from the Big Bang. When scientists study the CMB, they see small variations in temperature across the sky. These variations are incredibly small, but they match the predictions of inflation and quantum fluctuations. The pattern of these temperature differences is a direct result of the quantum fluctuations that were stretched and amplified during the early moments of the universe. Without these fluctuations, the universe might have remained perfectly uniform, with no galaxies, stars, or planets ever forming. But the implications of quantum fluctuations go even deeper. Some physicists suggest that quantum fluctuations could have been responsible for the very creation of the universe itself. In quantum mechanics, there is a concept called the uncertainty principle, which states that certain properties, like energy, can never be known with complete certainty. This allows for small, temporary violations of the usual rules of physics, such as energy appearing, for a brief moment, out of nowhere. These momentary energy fluctuations might have created the initial conditions that led to the universe's birth. Perhaps a quantum fluctuation in a pre-existing vacuum could have sparked the rapid inflation that created the universe. In this view, the universe didn't come from a singularity as described in the traditional Big Bang model, but rather from a quantum fluctuation that caused a region of space to suddenly expand. This expanding region could then have undergone inflation, eventually cooling and forming the universe as we see it today. This idea also ties into the theory of eternal inflation, where quantum fluctuations constantly create new regions of space that undergo their own inflationary periods, each potentially becoming its own universe. Our universe would then be just one bubble in an infinite, ever-expanding multiverse. In this model, quantum fluctuations not only sparked the creation of our universe, but they also continue to create new universes all the time. Quantum fluctuation challenges our understanding of cause and effect. In the classical world, every event has a clear cause, and one event leads to another in a predictable way. But in the quantum world, events can happen spontaneously, without a direct cause. This is part of what makes quantum mechanics so strange and difficult to understand. The idea that the entire universe could have arisen from a random, uncaused fluctuation is deeply counterintuitive. It suggests that the creation of the universe might not have required any specific cause or pre-existing conditions, but instead could have been a natural result of the unpredictable nature of quantum mechanics. Some scientists are trying to explore whether these ideas can be tested. One approach is to study the CMB in more detail, looking for subtle patterns that could provide more information about the quantum fluctuations that shaped the early universe. Many questions still remain. For instance, while quantum mechanics explains how fluctuations can occur, it's still not clear what caused the specific fluctuation that led to the creation of the universe. Some physicists suggest that the laws of quantum mechanics themselves might provide an answer, while others believe that there could be a deeper underlying theory that we have yet to discover. Emergence from a vacuum, the birth of energy. The idea of emergence from a vacuum is a fascinating topic that delves into the nature of energy and how it can appear from seeming nothingness. At its heart lies the concept of the quantum vacuum, a state that may seem empty, but is actually teeming with activity and potential. In the quantum world, the vacuum is not a simple void. It is filled with fluctuating energy fields that can give rise to particles and forces. To understand how energy can emerge from a quantum vacuum, we need to explore the nature of the vacuum itself. In classical physics, a vacuum is often described as a space devoid of matter and energy. However, in quantum mechanics, this definition changes significantly. The quantum vacuum is not empty. It is a dynamic arena where virtual particles constantly pop in and out of existence. These virtual particles are temporary fluctuations in energy that can never be observed directly, but they have real effects on the physical world. The energy that permeates the quantum vacuum is often referred to as vacuum energy. This energy is thought to be a fundamental aspect of the universe, influencing everything from the behavior of particles to the large-scale structure of the cosmos. According to quantum field theory, every type of particle corresponds to a field that exists throughout space. Even in the absence of particles, these fields have energy associated with them, which means that the vacuum itself can be a source of energy. One of the most intriguing consequences of vacuum energy is its relationship with gravity. The cosmological constant, a term originally introduced by Albert Einstein, is often associated with vacuum energy. In the framework of general relativity, vacuum energy contributes to the overall energy density of the universe, affecting its expansion rate. When vacuum energy is positive, it can act as a repulsive force, leading to accelerated expansion. This is a key aspect of current theories about dark energy, which is believed to make up a significant portion of the universe and drive its accelerated expansion. The idea that energy can emerge from a vacuum is not just a theoretical curiosity, it has real-world implications. For example, physicists have conducted experiments that demonstrate the effects of vacuum fluctuations. One well-known experiment is the Casimir effect, which involves two uncharged plates placed very close together in a vacuum. Due to the quantum fluctuations of the vacuum, the space between the plates has fewer virtual particles than the surrounding area, creating a pressure that pushes the plates together. This phenomenon highlights how vacuum energy can have tangible effects, even in seemingly empty space. In a broader sense, the emergence of energy from a quantum vacuum raises questions about the origins of the universe itself. If the universe can arise from vacuum fluctuations, then it suggests that the creation of energy and matter is a natural process governed by the laws of physics. Rather than needing an external force or cause to initiate the universe, the very fabric of space may contain the potential for energy to manifest spontaneously. This shifts our understanding of creation from a singular event to a continuous process influenced by the inherent properties of the quantum vacuum. This also opens up new possibilities for exploring the fundamental nature of reality. Some physicists propose that the universe may not have a singular origin point, but rather emerged from a more complex and interconnected structure. In this view, The vacuum itself could serve as a wellspring for the creation of multiple universes, each arising from its own fluctuations in energy, instead of a static backdrop against which events unfold. The vacuum could be an active participant in the creation of reality. The relationship between the vacuum and the birth of energy also invites scrutiny on the role of symmetry and breaking symmetry in particle physics. In many physical theories, the vacuum state represents a condition of symmetry, where forces and particles behave uniformly. However, when symmetries are broken, either through spontaneous processes or external influences, new particles and forces can emerge. This breaking of symmetry could be linked to the birth of energy and the subsequent formation of matter, as the underlying quantum vacuum transitions from a uniform state to one filled with diverse particles and forces. The laws of physics, could they be timeless? Traditionally, we think of the laws of physics as fundamental rules that govern how the universe operates. These laws, such as gravity, electromagnetism, and quantum mechanics, seem to apply consistently across space and time. But what happens when we consider the possibility that these laws existed before the universe itself came into being? To explore this idea, it is helpful to first examine what we mean by the laws of physics. In essence, these laws describe the relationships between different physical entities and how they interact with one another. For example, Newton's laws of motion describe how objects move in response to forces, while Einstein's theory of general relativity explains how mass and energy warp space-time. These laws have been tested and validated through countless experiments, giving us a reliable framework for understanding the behavior of the universe. However, they are rooted in our current understanding of space and time, which complicates the question of their existence prior to the universe's emergence. One of the most significant considerations in this discussion is the concept of time itself. Time, as we understand it, is a dimension in which events occur in a linear sequence from past to present to future. However, if we think about a time before the universe began, we encounter the challenge of imagining a state where time as we know it does not exist. In such a scenario, would the laws of physics still apply, or would they have no relevance in the absence of space and time? Some physicists and philosophers propose that the laws of physics could be a product of a deeper, more fundamental reality. In this view, the laws might emerge from more basic principles that govern the behavior of all things, even in a pre-universal state. For instance, string theory posits that fundamental particles are not point-like objects, but rather one-dimensional strings vibrating at different frequencies. This theory suggests a deeper framework that could exist outside of space and time, where the laws of physics are derived from the interactions of these strings. If this were the case, it might be possible for the laws of physics to exist in some form before the universe began. Another perspective comes from the field of quantum mechanics, which introduces uncertainty and probabilistic behavior at the fundamental level of particles. Quantum mechanics raises questions about determinism, the idea that every event has a definite cause. If the universe emerged from quantum fluctuations, as suggested in earlier discussions, then it implies a certain degree of randomness inherent in the very fabric of reality. This randomness could indicate that the laws of physics are not as fixed as we might think, allowing for the possibility that they could have evolved or changed over time, potentially existing in a different form before the universe's birth. Some theories in cosmology, like the cyclic model, suggest that the universe undergoes endless cycles of expansion and contraction. In this model, the universe could be born, expand, collapse, and then begin anew, creating a continuous cycle. If this were the case, the laws of physics would have to remain consistent throughout these cycles, reinforcing the idea that they could exist outside of any single incarnation of the universe. This suggests a more profound connection between the laws of physics and the nature of existence itself. As scientists explore these ideas, They often turn to fundamental questions about the universe's origins and the nature of reality. For example, the concept of a multiverse proposes that there could be multiple, perhaps infinite universes, each with its own set of physical laws. If this is true, it raises the question of whether the laws of physics are universal constants, or whether they can vary between different universes. If they can change, then what does that imply about their nature in the context of our own universe? Multiverse hypothesis. Was our universe one of many? One concept we keep coming back to in these theories is the multiverse hypothesis. This captivating idea suggests that our universe might not be the only one in existence. Instead, it posits that there could be countless other universes, each with its own unique properties, laws of physics, and histories. This notion challenges the traditional view of a singular universe and invites a radical rethinking of reality as we understand it. The concept of the multiverse arises from various branches of scientific thought, including cosmology, quantum mechanics, and string theory, each contributing to the notion that our universe is just one of many. One of the key motivations for considering the multiverse hypothesis comes from the observation of fine-tuning in the universe. Fine-tuning refers to the specific conditions that allow for the existence of life as we know it. The fundamental constants of nature, such as the strength of gravity, the electromagnetic force, and the mass of particles, seem to be remarkably precise. If any of these constants were even slightly different, the universe could not support life. This has led scientists and philosophers to ponder why our universe has these precise conditions. One potential explanation is that there are many universes, each with different values for these constants. In this scenario, we just happen to live in one of the few universes where conditions are suitable for life. The idea of the multiverse has roots in quantum mechanics, particularly in the many worlds interpretation. This interpretation suggests that every time a quantum event occurs, the universe splits into multiple branches, each representing a different outcome. For instance, if a particle can exist in two states, one universe would reflect one state, while another universe would reflect the alternative state. This branching leads to a vast number of parallel universes, each unfolding its own unique history. In this view, every choice made and every event occurring in our universe could give rise to an entirely new universe, creating an almost infinite tapestry of realities. Cosmic inflation, a theory that describes the rapid expansion of the universe shortly after the Big Bang, also supports the multiverse hypothesis. During inflation, tiny quantum fluctuations were stretched to cosmic scales, creating variations in the density of matter throughout the universe. Some regions may have stopped inflating, while others continued, leading to a bubble-like structure where different regions of space can have varying properties. Each bubble could develop its own set of physical laws and constants, resulting in a multitude of universes within a larger multiverse framework. In this model, our universe is just one bubble among many, each potentially harboring different forms of life and physical laws. String theory also enriches the multiverse concept by suggesting that the fundamental particles of nature are not point-like objects, but rather tiny, vibrating strings. This theory allows for the existence of multiple dimensions beyond the familiar three-dimensional space we experience. As strings vibrate in different ways, they can give rise to various particles and forces. Moreover, string theory permits many possible configurations of these extra dimensions, leading to different sets of physical laws. This vast array of possibilities suggests that there could be a multitude of universes, each with its own unique characteristics, existing simultaneously. However, while the multiverse hypothesis is an exciting idea, it is not without its challenges and controversies. One significant issue is the difficulty in testing or observing other universes. Science relies on empirical evidence and reproducibility, but the multiverse, by its nature, may just be inherently unobservable. Critics argue that because other universes may be completely separate from our own, we may never find evidence to support their existence. Some proponents of the multiverse hypothesis argue that it can be indirectly supported through the fine-tuning problem. If the multiverse is true, then the specific conditions of our universe would be one among many outcomes. This perspective can make sense of why our universe appears fine-tuned for life. We are simply one of the few lucky universes where conditions happened to align perfectly. While this does not provide direct evidence for the multiverse, it offers a framework for understanding why our universe has its specific characteristics. Another point of contention lies in the implications of a multiverse for our understanding of existence. If there are infinitely many universes, what does that mean for our sense of identity and reality? Some philosophers argue that if every possible outcome exists somewhere in the multiverse, it diminishes the uniqueness of our experiences and choices. Others, however, find this notion liberating, as it suggests a broader reality where anything is possible. The multiverse hypothesis raises many questions about determinism and free will. If every choice leads to a branching universe, does this mean that our decisions are predetermined, or do we still have agency within our universe? The philosophical implications are profound and provoke deep contemplation about the nature of consciousness, choice, and existence itself. Eternal inflation, a never-ending cosmos. The theory of eternal inflation proposes the cosmos might never have a true beginning or an end, but instead exists in a state of continuous expansion, always forming new universes. This idea is an extension of the cosmic inflation theory, which describes a period of rapid expansion that occurred in the early moments of our universe's history. However, in the case of eternal inflation, this expansion doesn't stop. It continues in some regions of space indefinitely, creating a potentially infinite number of new universes, each with its own unique characteristics. To understand eternal inflation, it's helpful to revisit the concept of inflation. According to the inflationary model, after the Big Bang, the universe underwent a brief but extraordinarily rapid expansion. This phase of inflation smoothed out the universe, explaining why space looks nearly uniform in every direction we observe. Inflation also stretched tiny quantum fluctuations to cosmic scales, seeding the formation of galaxies and large-scale structures in the universe. Once inflation ended, the universe transitioned into the slower, more gradual expansion that continues to this day. In the eternal inflation model, however, this inflationary process doesn't end everywhere at once. Some regions of space stop inflating and form individual universes like ours, while other regions continue to expand at an accelerated rate. In this way, the cosmos is always inflating in some areas, continuously spawning new pocket universes or bubble universes. Each of these bubble universes could have its own distinct set of physical laws, constants, and even dimensional structures. Our universe would be just one of these countless bubbles surrounded by a vast, eternally inflating cosmos. Eternal inflation shifts how we view the universe. Instead of a singular event, such as the Big Bang, marking the beginning of everything, it suggests that inflation is an ongoing process. This view aligns with the multiverse hypothesis, implying that new universes are constantly being born in a never-ending cycle. While we may observe the finite boundaries of our own universe, the broader inflating cosmos extends beyond what we can see, filled with countless other universes forming and evolving in their own ways. It also raises intriguing questions about the nature of time. In our universe, we experience time as linear, moving from the past to the present to the future. But in the eternal inflation model, the concept of time becomes more complex. The inflating regions of space exist in a state that defies the usual flow of time, always expanding and creating new universes without ever reaching an endpoint. This introduces the possibility that inflation could have been happening infinitely into the past, as well as into the future. In this scenario, there may never have been a true beginning to the cosmos in the way we traditionally think of it. Quantum fluctuations also play a critical role in the eternal inflation model. As space continues to expand at an exponential rate, tiny quantum fluctuations are stretched and magnified. These fluctuations create regions where inflation slows down or stops, forming new bubble universes. But in the broader inflating space, other fluctuations continue to drive expansion forward. The result is a dynamic and chaotic process where new universes are born in an ongoing cycle, shaped by the random fluctuations at their origins. One of the most intriguing aspects of eternal inflation is the idea that each universe it spawns could have its own unique set of physical laws. In our universe, we are governed by the constants and laws that we have measured and understood, such as the speed of light, the strength of gravity, and the behavior of particles. But in another bubble universe, these values could be different. Some universes might have stronger gravity, while others could have entirely different types of particles or forces. The range of possibilities is vast, and it opens the door to a nearly infinite variety of potential universes, each with its own unique structure and history. This diversity among universes also becomes the explanation for the anthropic principle, which suggests that we observe the universe as it is because we exist in it. Out of the countless bubble universes, only a small fraction may have the right conditions for life to form. In most other universes, the physical constants may not allow for the development of stars, planets, or living organisms. But in our universe, the conditions are just right for life to exist, which is why we find ourselves here, observing it. Again, however, this theory is hard to test because with our current understanding of physics, it appears we are limited to observing only our own universe, with no direct access to the others. This makes it difficult to gather empirical evidence that could confirm or refute the theory. Another challenge with eternal inflation is the so-called measure problem, which refers to the difficulty in calculating probabilities in an infinite multiverse. If eternal inflation produces an infinite number of universes, how can we make meaningful statistical predictions about the likelihood of various outcomes? This issue complicates efforts to apply conventional scientific reasoning to the multiverse, where infinities arise in many different ways. Despite these challenges, the theory of eternal inflation continues to inspire scientific inquiry. Researchers are exploring ways to indirectly detect evidence of other universes, such as looking for imprints in the CMB radiation, which might show signs of collisions between bubble universes. While such evidence remains speculative, it is a promising area of investigation. Brain cosmology, the clash of higher dimensional universes. A more mind-bending theory is brain cosmology, which is a concept out of string theory, one of the leading ideas in modern theoretical physics. According to string theory, the fundamental building blocks of the universe are not point-like particles, but tiny vibrating strings. These strings can exist in multiple dimensions, beyond the three spatial dimensions and one-time dimension that we experience in everyday life. In this framework, brains, short for membranes, are higher dimensional objects that can exist in multiple dimensions as well. These brains, according to brain cosmology, might be responsible for the creation of entire universes. One of the most fascinating ideas in brain cosmology is that universes like ours could be the result of collisions between brains. Imagine two immense multidimensional brains drifting through a higher dimensional space. These brains are not part of the universe we see, but exist in an extra-dimensional bulk, a space that contains multiple brains. When two of these brains collide, the impact could release an enormous amount of energy, sparking the birth of a new universe. This new universe, formed by the clash of brains, could resemble our own universe, with its own physical laws and structure. This idea shifts the traditional perspective on the Big Bang, suggesting that what we see as the birth of our universe could actually be the result of a higher dimensional event. In this sense, the Big Bang might not have been a unique one-time event, but part of a larger cycle of brain collisions. The idea of brain cosmology also stems from the concept that our universe may be a three-dimensional brain floating in this higher dimensional bulk. While we are confined to the three dimensions of our universe, higher dimensions could exist beyond our perception. In this picture, our universe is like a soap bubble in a vast sea of other brains. We can only observe and interact with things that exist on our own brain, but there could be other brains floating nearby, each hosting its own universe. One of the key questions in brain cosmology is how these brains move and interact in the higher dimensional space. In string theory, these brains can move freely in certain dimensions, but they may also be attracted or repelled by other brains. When two brains come close to each other, their interaction could lead to a collision. The energy released from such a collision would be immense, enough to create a universe like ours. In this view, the creation of universes could be a natural consequence of the dynamics of brains in a higher dimensional space. It also helps to explain some of the mysteries in modern cosmology. For example, the universe's expansion rate is accelerating, something attributed to a mysterious force called dark energy. In brain cosmology, dark energy might be the result of the tension between brains in the higher dimensional bulk. As brains move through this space, they could influence each other's dynamics, causing effects that we interpret as dark energy within our universe. Brain collisions might also explain the homogeneity of the universe, the fact that it appears largely the same in all directions. The energy released from a brain collision could quickly smooth out any initial irregularities, leading to the relatively uniform structure we observe today. An intriguing implication of brain cosmology is the possibility of interactions between universes. While each brain hosts its own universe, it's possible that brains could come close enough to each other to influence one another. Some scientists have speculated that certain gravitational effects or other anomalies we observe in our universe might be the result of interactions with nearby brains. If another universe exists on a brain close to ours, it might exert a small gravitational pull, causing effects that we could potentially detect. Testing the ideas of brain cosmology is extremely difficult, because these extra dimensions and brains lie beyond our current ability to observe directly. However, researchers are exploring indirect ways to investigate the theory. For instance, particle accelerators like the Large Hadron Collider might be able to detect signs of extra dimensions by observing how particles behave at extremely high energies. If particles suddenly seem to vanish or exhibit unexpected behavior, it could be a sign that they are interacting with the higher dimensional space or with other brains. Cyclic universe models, time without a beginning. The cyclic universe model, on the other hand, suggests that the universe may not have a singular beginning or end, but instead exists in a repeating loop of expansions and contractions. According to this idea, the universe could go through endless cycles, where each period of expansion, like the one we currently live in, is followed by a contraction, which eventually leads to a new expansion phase. This concept challenges the traditional view of the Big Bang as the ultimate beginning of everything, and instead presents time as infinite, with no true start or finish. The idea of a cyclic universe is not new. In fact, ancient cosmologies often envisioned the universe as eternal, with creation and destruction occurring in a continuous loop. For example, Hindu cosmology describes a cycle of creation and destruction, where the universe is born, lives, dies, and is reborn in an ongoing process. Similarly, some ancient Greek philosophers speculated about a universe that experiences recurring cycles. These early ideas, while based on mythological or philosophical views, share a key theme with modern cyclic universe models: the notion that time and existence could be eternal without a definitive beginning. In modern cosmology, the cyclic universe gained renewed interest through theories that attempt to explain how the universe could avoid a singular starting point, like the Big Bang, and instead operate in a repeating cycle. One of the most prominent cyclic models is based on the idea of a big bounce rather than a Big Bang. In this model, the universe expands for billions of years, but instead of continuing to expand forever, it eventually slows down, reverses, and contracts. As the universe contracts, it shrinks back into an incredibly dense state, similar to what we think of as the Big Bang. But instead of ending in a singularity, the contraction bounces into a new phase of expansion, restarting the universe in a new cycle. The cyclic universe model could help answer some long-standing questions in cosmology. It provides a solution for the question of what happened before the Big Bang. Cyclic models offer an answer by suggesting that the Big Bang was not a unique event, but just the latest phase in an ongoing sequence of expansions and contractions. Each time the universe contracts and bounces back, it begins a new cycle. So there is no need for a singular beginning in the sense that we traditionally think of it. This model also attempts to address some of the puzzles of modern cosmology, such as the nature of dark energy and the ultimate fate of the universe. Currently, observations show that the universe is not only expanding, but that this expansion is accelerating, driven by a mysterious force called dark energy. In a cyclic model, dark energy could play a key role in the universe's expansion and eventual contraction. Some theories propose that dark energy is not constant but changes over time. In this scenario, dark energy could initially cause the universe to expand rapidly, but as it weakens or changes in character, it could allow the universe to slow down and contract, starting the next cycle. Another key feature of cyclic models is that they offer an alternative to the idea of a heat death of the universe. In the traditional view, if the universe continues expanding forever, it will eventually become cold and empty, with all stars burning out and matter spreading so thin that nothing new can form. This is known as the heat death scenario, where the universe reaches a state of maximum entropy with no usable energy left. In a cyclic universe, however, this ultimate fate is avoided. Instead of expanding forever and reaching a lifeless cold end, the universe would eventually contract, reversing the process and allowing for the possibility of new structures and stars forming in the next cycle. One of the challenges with cyclic models is explaining how the universe can go through an infinite number of cycles without increasing entropy each time. Entropy is the measure of disorder in a system, and according to the second law of thermodynamics, entropy in a closed system tends to increase over time. In a universe that goes through repeated cycles, this could mean that with each bounce, the universe would become more disordered. So, versions of the cyclic model propose mechanisms by which entropy is reset or controlled during each cycle. For instance, during the bounce phase, new physics might come into play that allows the universe to reset its entropy, making each new cycle fresh and avoiding a buildup of disorder over time. Recent developments in string theory and quantum gravity have contributed to the exploration of cyclic models. In some versions of string theory, the universe exists in a higher dimensional space where brains can collide, triggering the birth of a new universe. These collisions could serve as the bounce mechanism in a cyclic universe, providing a natural explanation for how each cycle begins. The interplay between quantum mechanics, gravity, and extra dimensions offers new ways to think about how the universe could avoid a singular beginning and instead operate in a continuous, eternal cycle. An aspect of the cyclic universe is for the possibility of new universes to emerge with different properties after each bounce. While the physical laws in our universe seem fine-tuned for life, cyclic models raise the possibility that each new cycle could produce slightly different conditions. Some cycles might create universes with stronger gravitational forces or different physical constants, while others might produce conditions similar to our own. In this cyclical model, time could be seen as having no start or end, but rather as an infinite loop, where each moment is connected to a larger ongoing process. This challenges our traditional view of time as linear, with a distinct past, present, and future. Instead, time might be more like a circle, with each phase of the universe's expansion and contraction feeding into the next, without a clear origin point. The holographic universe. Could the Big Bang be a projection? The holographic universe is a theory that suggests the entire universe, including the space we live in and everything we experience, could be a projection of information stored on a distant two-dimensional surface. This idea might seem strange at first, but it has its roots in one of the most successful theories in physics, quantum mechanics. The holographic principle proposes that all the information contained in a three-dimensional region of space could be encoded on a flat surface that surrounds it, much like a hologram. In this view, our three-dimensional universe is not what it appears to be, but rather a projection from a lower-dimensional reality. The origins of this idea come from black hole physics. In the 1970s, scientists began to study what happens to information when it falls into a black hole. According to classical physics, anything that crosses the event horizon of a black hole, including light and matter, is lost forever. However, this seemed to contradict the laws of quantum mechanics, which suggest that information cannot be destroyed. To resolve this paradox, physicist Stephen Hawking and others suggested that the information might not be lost inside the black hole itself, but could instead be stored on the event horizon, the two-dimensional boundary surrounding the black hole. In this way, the three-dimensional information about the black hole's contents could be encoded on its two-dimensional surface. This idea was later expanded to apply to the entire universe. If the information inside a black hole could be encoded on a two-dimensional surface, perhaps the same could be true for the universe as a whole. This is where the holographic principle comes into play. The theory suggests that the entire three-dimensional universe could be described by information encoded on a two-dimensional boundary far away from us, possibly at the edges of the observable universe. In this sense, what we perceive as a three-dimensional reality might actually be a hologram projected from this distant surface. According to some versions of the theory, the Big Bang itself might not have been the true beginning of the universe, but rather the moment when the projection of the universe we experience began. The information that makes up our universe could have existed on this two-dimensional surface before the Big Bang, and was projected into the three-dimensional universe we observe today. In this view, the Big Bang was not the origin of everything, but a transition from a lower-dimensional reality to the three-dimensional world we know. One of the implications of the holographic universe is that space and time, as we understand them, might not be fundamental. Instead, they could emerge from the interactions of information on this distant two-dimensional surface. This would mean that the fabric of the universe, including the dimensions we experience, is not as solid or real as it appears. Instead, space and time could be the result of deeper underlying processes that take place on the holographic boundary of the universe. The holographic principle also has the potential to unite two major theories in physics: quantum mechanics and general relativity. These two theories describe the universe on very different scales, with quantum mechanics explaining the behavior of particles at the smallest levels and general relativity describing the large-scale structure of space, time, and gravity. So far, scientists have struggled to find a theory that combines these two views of the universe. The holographic principle could provide a way to bring them together by suggesting that gravity and space-time emerge from quantum processes taking place on a two-dimensional surface. Another interesting aspect of the holographic universe is that it offers a new perspective on the problem of dark matter and dark energy, two mysterious components that make up most of the universe's mass and energy. Some versions of the holographic principle suggest that what we call dark matter and dark energy might not be stuff at all, but rather artifacts of the projection from the two-dimensional boundary. In this view, the strange behavior of galaxies and the accelerated expansion of the universe might be explained by how the information on the holographic boundary is projected into the three-dimensional space we observe. The holographic universe theory remains speculative, and there is much work to be done before it can be fully tested or confirmed. However, researchers are exploring ways to investigate the theory through experiments. A potential area of investigation is the behavior of particles at extremely high energies. If the holographic principle is correct, then at very small scales, the universe might behave differently than we expect based on our current understanding of space and time. Particle accelerators or large space telescopes could offer clues by observing how particles interact under extreme conditions, potentially revealing evidence that supports or contradicts the holographic model. Quantum gravity, the missing link to a pre-Big Bang reality. Quantum gravity is one of the biggest puzzles in modern physics, as it represents the effort to reconcile two fundamental yet seemingly incompatible theories, quantum mechanics and general relativity. While quantum mechanics describes the behavior of particles at the smallest scales, general relativity governs the large-scale structure of space and time. The problem is that these two theories break down under extreme conditions, such as those that would have existed in the moments before and during the Big Bang. Quantum gravity seeks to unite them, offering a single framework to explain both the vastness of the cosmos and the tiniest particles that make it up. What makes quantum gravity particularly exciting is its potential to unlock the mysteries of what happened before the Big Bang. At present, our understanding of the universe begins with the Big Bang, a moment when the universe was incredibly hot, dense, and small. Yet beyond that point, general relativity no longer applies because the gravitational forces become so extreme that space and time themselves become unstable. To understand what happened before this moment, or even if before has any meaning in such a scenario, we need a theory of quantum gravity. Several approaches to quantum gravity have been proposed, with string theory and loop quantum gravity being among the most well-known. String theory introduces the idea of extra dimensions beyond the familiar 3 dimensions of space and 1 of time. If these extra dimensions exist, they could offer insights into what may have existed before the Big Bang, suggesting that the Big Bang might not have been the true beginning of everything, but rather a phase in a larger, more complex system. Loop quantum gravity takes a different approach by attempting to quantize space itself. Instead of treating space as a smooth continuum, this theory suggests that space is made up of tiny, discrete units, much like the pixels on a TV or phone screen. If space is quantized in this way, it could help explain what happens to space and time at the incredibly small scales involved in the Big Bang. According to some versions of loop quantum gravity, the Big Bang could have been preceded by a big bounce, where the universe contracts to a certain point and then bounces back, avoiding the need for a singularity where the laws of physics break down. One of the key challenges in developing a theory of quantum gravity is that it operates at energy scales far beyond anything we can currently observe. The particles and forces involved are so small and so energetic that we lack the technology to directly probe them. However, indirect evidence and mathematical models suggest that quantum gravity could offer explanations for the behavior of the universe at its earliest moments. For example, some theories predict that quantum fluctuations in the fabric of space and time could have triggered the Big Bang itself. These fluctuations, though tiny, could have set off a chain reaction leading to the expansion of the universe we see today. It could also help explain the mysterious properties of black holes, which share some similarities with the conditions present at the Big Bang. Inside a black hole, gravity becomes so strong that it warps space and time to a point where general relativity breaks down, just as it does in the early universe. By understanding how quantum gravity applies to black holes, scientists could potentially gain insights into the nature of space and time at the universe's inception. Another outcome of quantum gravity research is the discovery that time itself might be a more fluid or emergent property than we currently understand. In our everyday experience, time flows in one direction, from the past to the future. But quantum mechanics introduces the possibility that time could behave differently at the smallest scales. Some theories suggest that time might not exist in the conventional sense at the quantum level, or that it could be linked to the geometry of space in ways we don't yet fully understand. This could provide a fresh perspective on what before the Big Bang might mean if time itself was created in the Big Bang event. In addition to shedding light on the universe's earliest moments, quantum gravity could help us address some of the unresolved questions in modern cosmology, such as the nature of dark energy and dark matter. These two phenomena make up a large chunk of the universe's mass, energy and source of gravity, yet understanding their true nature still eludes us. Some versions of quantum gravity suggest that these puzzling aspects of the universe could be linked to the deeper structure of space and time, offering potential explanations for their behavior. Dark energy and dark matter, hidden clues to our origins. Dark energy and dark matter are two of the biggest mysteries in the universe, making up the vast majority of its total content. Yet, despite their influence, we know surprisingly little about what they are or how they behave. These invisible forces don't emit or absorb light like the matter we can see, making them difficult to detect directly. However, their effects on the cosmos are undeniable. Scientists believe that understanding these strange components could provide valuable clues, not only about the current state of the universe, but also about its origins, and potentially what existed before the Big Bang. Dark matter accounts for about 27% of the universe's mass and energy. It doesn't interact with light, which is why it's called dark, but it has a powerful gravitational pull. We know it's there because we can see its effects on galaxies and galaxy clusters. Without dark matter, galaxies wouldn't hold together as they do. The stars would drift apart. Despite its critical role, dark matter has remained elusive. We don't know exactly what it's made of, though there are several competing theories. Some suggest it could be made of weakly interacting massive particles, WIMPs, while others propose that dark matter could consist of smaller, more exotic particles that don't interact with normal matter at all, except through gravity. Because dark matter plays such an essential role in the structure of the universe, understanding it could help explain how galaxies and other large cosmic structures formed after the Big Bang. More intriguingly, it could also offer insights into what came before. If dark matter existed before the Big Bang, it might have influenced the conditions that led to the universe's expansion. Some theories suggest that dark matter could have originated in a previous phase of the universe, or even in a different universe entirely, bringing with it clues about pre-Big Bang physics. If we could unravel the mystery of dark matter, we might learn whether its presence or behavior points to something that existed before our universe as we know it. Dark energy, which makes up around 68% of the universe's mass energy content, is an even stranger force. Unlike dark matter, which pulls things together through gravity, dark energy has the opposite effect. It pushes the universe apart. This mysterious force is responsible for the accelerated expansion of the universe, a discovery that shook the scientific community in the late 20th century. The fact that the universe isn't just expanding, but doing so at an increasing rate, suggests that dark energy plays a crucial role in the long-term fate of the cosmos. While we know dark energy exists, we don't fully understand its origin or nature. Some scientists propose that dark energy could be tied to the vacuum of space itself, perhaps arising from quantum fluctuations. These fluctuations are tiny, temporary changes in energy that occur even in empty space, and they could create a form of energy that permeates the universe, causing it to expand. This concept links dark energy to the quantum realm, suggesting that the same forces that influence particles at the smallest scales could also govern the universe's largest structures. If dark energy is indeed related to quantum fluctuations, it might offer a clue to what happened before the Big Bang. Quantum mechanics suggests that space itself isn't completely empty, but is instead filled with constant activity at the smallest scales. In this view, the universe could have emerged from a quantum foam, a seething dynamic state in which particles and energy pop in and out of existence. Some theorists speculate that dark energy might have played a role in triggering the expansion of this quantum foam into the universe we observe today. Another possibility is that dark energy is connected to other dimensions or universes. In some models of the multiverse, dark energy might leak into our universe from other dimensions, influencing the rate of cosmic expansion. This could suggest that our universe is part of a larger system, where different universes interact in subtle ways. If this is the case, dark energy could offer a bridge to understanding the broader context in which our universe exists and potentially provide hints about what came before the Big Bang. The arrow of time. Does time flow differently, beyond the Big Bang? Time, as we experience it, seems to flow in one direction, from the past to the future. This one-way flow is often called the arrow of time. It governs much of what we observe in the universe, from the way objects move to how processes unfold. On a human level, time's passage is marked by the irreversible progression of events. Yet, when scientists examine the deepest mysteries of the universe, they begin to wonder, does time always behave this way? Could time have flowed differently before the Big Bang? Or did time itself only begin with the universe's creation? In physics, the arrow of time is closely tied to the second law of thermodynamics, which states that in any closed system, entropy, or disorder, always increases over time. This is why certain processes, like mixing milk into coffee or breaking an egg, are irreversible. The increasing disorder gives time a direction, pointing from a low entropy past to a higher entropy future. However, when scientists examine the laws of physics that govern the universe at its most fundamental level, they find that these laws are mostly time-symmetric. This means that, at least in theory, many physical processes could happen in either direction, forward or backward in time. This raises an interesting question. If the laws of physics don't care which way time flows, why does time appear to move in only one direction for us? The answer seems to lie in the initial conditions of the universe. The Big Bang, which marked the beginning of the observable universe, was a moment of incredibly low entropy. The universe started in a highly ordered state, and as it expanded and evolved, its entropy increased, giving rise to the arrow of time we experience. But if the arrow of time is linked to the universe's initial conditions, what does that say about time before the Big Bang, or whether time even existed before? Some have suggested that time itself may be an emergent property, something that came into existence with the birth of the universe. In their view, time didn't exist before the Big Bang, because there was no before in the conventional sense. The very concept of time could have been created in the same moment as the universe, emerging along with space, energy, and matter. If this is true, then asking what happened before the Big Bang might be like asking what's north of the North Pole. It's a question that doesn't make sense because time simply didn't exist until the universe began. There are also some intriguing ideas in theoretical physics that suggest the arrow of time could flow differently or even reverse under certain conditions. One hypothesis is that in the distant future, when the universe reaches a state of maximum entropy, the arrow of time could reverse. In this scenario, time could flow backward and the universe might start to contract instead of expand. While this idea is speculative, it opens up fascinating possibilities about the nature of time and its relationship to the universe's life cycle. Another idea is that time could behave differently in other regions of the multiverse. If our universe is just one of many in a larger multiverse, then time in other universes might not flow in the same way. Some universes could experience time flowing in reverse, while others might have no concept of time at all. These possibilities challenge our understanding of what time is and how it behaves, suggesting that it might be more flexible and less universal than we imagine. The idea that time is emergent is also linked to theories about quantum gravity and the nature of space itself. In some versions of quantum gravity, space and time are not fundamental aspects of reality, but rather emergent properties that arise from more basic underlying processes. If time emerges from the quantum fabric of the universe, then it might have only come into existence when the universe reached a certain level of complexity, possibly at or just after the Big Bang. This would mean that time as we know it is a byproduct of the universe's evolution, rather than a fundamental feature of reality. Even though these ideas remain speculative, they point to a deeper truth. Our understanding of time is still limited. The flow of time is something we experience in everyday life, but at the level of the universe's creation and its most fundamental laws, time becomes a more mysterious and elusive concept. By studying how time behaves in extreme conditions, such as near black holes or during the early moments of the Big Bang, scientists will hopefully uncover more about its nature. Cosmic echoes. Can we detect signals from a pre-Big Bang universe? The universe is filled with faint traces of its early moments, the most famous being the cosmic microwave background or CMB radiation. This radiation is a relic from about 380,000 years after the Big Bang, when the universe had cooled enough for atoms to form, allowing light to travel freely through space. It's a snapshot of the universe in its infancy, and studying it has helped scientists piece together the early stages of cosmic history. But some researchers wonder if these cosmic echoes might carry even deeper secrets, perhaps clues about what happened before the Big Bang. The cosmic microwave background is remarkably uniform, but there are tiny fluctuations, small variations in temperature that reveal patterns in how matter was distributed in the early universe. Some scientists have speculated that these patterns might contain imprints from a time before the Big Bang. If there was something before our universe began, whether it was a previous universe or some other kind of pre-Big Bang state, it might have left behind subtle hints in the structure of space and time. The challenge is identifying these imprints and distinguishing them from other processes that shaped the early universe. One idea is that the geometry of space-time itself could offer clues about pre-Big Bang conditions. The shape and structure of the universe are governed by Einstein's theory of general relativity, which tells us how matter and energy warp space and time. If there were events or states that preceded the Big Bang, they might have altered the geometry of space-time in ways that we could detect today. For example, some models suggest that our universe might have bounced into existence after a previous phase of contraction. In these models, the geometry of space-time could contain traces of this earlier phase, potentially visible in the distribution of matter and energy in the universe today. Another potential source of pre-Big Bang signals could be found in singularities, points in space where the laws of physics break down. Black holes, which are regions where gravity becomes so intense that not even light can escape, contain singularities at their cores. Some researchers have speculated that black holes could be linked to pre-Big Bang physics. In certain theories, black holes might act as gateways between different phases of the universe, or even between different universes in a multiverse. If we could better understand what happens at the center of a black hole, we might unlock new insights into the physics that governed the universe before the Big Bang. There's also the possibility that some black holes could have formed right after the Big Bang itself. These so-called primordial black holes might have survived the universe's explosive beginning and could still exist today, scattered throughout the cosmos. Detecting these ancient black holes could offer a glimpse into the earlier stages of our universe's beginning, perhaps providing a direct connection to pre-Big Bang conditions. Though finding primordial black holes remains a challenge, the discovery of such objects would revolutionize our understanding of cosmic history. Apart from black holes, the very nature of space-time at the quantum level could hold the key to understanding what came before the Big Bang. Quantum mechanics suggests that space and time might not be continuous and smooth as they appear to us, but rather made up of tiny, discrete units. This idea, known as quantum gravity, could provide insights into how the universe transitioned from a pre-Big Bang state into the rapidly expanding universe we see today. If space-time has a quantum structure, it's possible that echoes of pre-Big Bang conditions might be hidden in the way space and time behave at the smallest scales. Detecting signals from a pre-Big Bang universe remains a daunting challenge, but some researchers are exploring new techniques to search for these cosmic echoes. One approach involves looking for unusual patterns in the CMB, such as circular features that might indicate collisions between our universe and other universes in the multiverse. Another possibility is to study gravitational waves, ripples in space-time caused by violent cosmic events. If pre-Big Bang events generated gravitational waves, these signals could still be detectable today, offering a direct glimpse into the conditions that existed before the Big Bang. Vacuum decay. Could the universe have formed from a false vacuum? One of the more intriguing theories in modern cosmology suggests that the universe could have originated from something known as a false vacuum. The idea behind this hypothesis involves vacuum decay, a process in which the universe transitions from one energy state to another, more stable one. In this scenario, the universe may not have started from nothing, but rather emerged from a shift in the structure of space itself, a phase transition that fundamentally altered the fabric of reality. To understand this theory, it's essential to grasp the concept of a vacuum in physics. In quantum mechanics, a vacuum isn't truly empty. Instead, it's filled with fluctuating energy fields, where particles can momentarily pop in and out of existence. This quantum vacuum has an energy associated with it, which is crucial to the vacuum decay theory. In the context of vacuum decay, there are two kinds of vacuums: the false vacuum and the true vacuum. A false vacuum is a state that appears stable but isn't the lowest possible energy state. Think of it like a marble sitting in a shallow dip on a hill. It seems to be at rest, but with just the right push, it could roll down into a deeper, more stable dip. In cosmology, this metaphor applies to the state of space itself. The universe might have started in a high-energy, false vacuum state, and eventually, it transitioned to a lower-energy, true vacuum through a process known as a phase transition. This phase transition is thought to have been violent and rapid, potentially creating the universe we observe today. Just as water changes from a liquid to a gas during boiling, the false vacuum could have undergone a dramatic shift, releasing energy and triggering the rapid expansion of space, a process closely tied to cosmic inflation. Inflation is the idea that in the earliest moments of the universe, space expanded at an extraordinarily fast rate. The vacuum decay theory offers a possible explanation for what could have caused this rapid expansion. The transition from a false vacuum to a true vacuum would have released a tremendous amount of energy, possibly enough to create all the matter and energy in the universe. This sudden release could have driven the expansion of space and set the stage for the formation of galaxies, stars, and planets. In this view, the universe wasn't created from nothing in a literal sense, but rather from the energy that was released when the vacuum state of space changed. This idea aligns with the broader framework of quantum field theory, where fields and vacuums are seen as fundamental to the structure of the universe. One of the striking aspects of this theory is that it suggests that the universe might have existed in some form before the Big Bang, albeit in a very different state. The false vacuum could have been a long-standing feature of the cosmos, with the universe sitting in a high-energy state until something, perhaps a quantum fluctuation or some external event, triggered the transition to a lower-energy, true vacuum. This event would then mark the beginning of the universe as we know it, but not necessarily the beginning of everything. In addition to explaining the universe's origins, the vacuum decay hypothesis raises fascinating questions about the universe's future. If our universe emerged from a false vacuum, it's possible that we're currently living in a false vacuum again. This would mean that while the universe appears stable, it could still transition to an even lower energy state at some point in the future. Such a transition, if it occurred, would have dramatic consequences. It could trigger another phase of rapid expansion. Or worse, it could destroy the universe as we know it, replacing it with a new, radically different reality. While the idea of vacuum decay as a threat to the universe's future may sound alarming, it's important to note that there's no evidence this will happen anytime soon. The false vacuum, if we're indeed in one, might remain stable for billions or even trillions of years. The process that could trigger vacuum decay, if it happens at all, would likely take place on timescales far beyond human comprehension. Additionally, because the universe is so vast, A vacuum decay event would likely begin in one small region of space and take an enormous amount of time to spread, so it wouldn't happen instantly on a cosmic scale. Beyond its implications for the future, the vacuum decay hypothesis also leads us to wonder what could have triggered the phase transition that created the universe. In quantum field theory, transitions between different vacuum states can be caused by quantum fluctuations, random changes in energy that occur in empty space. These fluctuations are unpredictable but could, in theory, cause a false vacuum to decay. If this is what happened in the early universe, then a random fluctuation in the vacuum energy might have been enough to push the universe from a high-energy false vacuum into the lower-energy true vacuum state, causing the phase transition that led to the universe's rapid expansion. Another possibility is that the universe existed in a state of eternal inflation before the vacuum decay event occurred. In the theory of eternal inflation, regions of space undergo inflation indefinitely, with some parts transitioning to lower energy states and forming new universes. Our universe might be one of many that emerged from this process, with the phase transition that created our universe being just one event in a much larger multiverse. In this view, vacuum decay would be a common occurrence, constantly creating new universes from the false vacuum of space. Primordial quantum entanglement. Did the universe begin entangled? Quantum entanglement is one of the most puzzling and intriguing aspects of quantum mechanics. It describes a phenomenon where two or more particles become linked in such a way that the state of one instantly influences the state of the other, no matter how far apart they are. This connection between particles, which Albert Einstein famously called spooky action at a distance, defies classical physics expectations of locality, how objects interact based on their proximity. Entanglement plays a crucial role in the behavior of quantum systems, and some researchers suggest that it may also hold clues about the origins of the universe itself. The idea of primordial quantum entanglement proposes that, in the earliest moments of the universe, all particles were entangled with each other in a highly interconnected state. This idea stems from the fact that the universe was once much smaller and denser, a point when all matter and energy were compressed into an incredibly tight space. As the universe expanded following the Big Bang, it's possible that particles remained entangled, even as they moved apart. This would mean that the large-scale structure of the universe today might still reflect the quantum connections that were formed at the universe's birth. In the first moments after the Big Bang, when the universe was a hot, dense soup of particles, quantum mechanics dominated the behavior of matter. Everything was packed tightly together, and quantum effects like entanglement would have been incredibly important. As the universe expanded, quantum entanglement may have persisted across large distances, potentially influencing the distribution of matter on cosmic scales. This could explain some of the uniformity we see in the universe today, such as why regions of space that are now far apart appear to have been influenced by the same initial conditions. One intriguing possibility is that quantum entanglement could stretch not just across the visible universe, but between different universes in a larger multiverse. If multiple universes emerged from the same quantum system, they could be entangled with each other in a way that influences their development. This would mean that our universe is not an isolated entity, but rather part of a larger, interconnected system of universes, all sharing quantum information. The idea of entanglement stretching across universes introduces the possibility that the laws of physics in our universe might be connected to events in other universes. Quantum entanglement in the early universe could also help explain some of the strange behavior we observe in quantum systems today. For example, when scientists conduct experiments with entangled particles, they find that changing the state of one particle instantly affects the other, regardless of the distance between them. This instantaneous connection seems to violate the speed of light as the ultimate speed limit, something that classical physics relies on. But in a universe that began in a state of primordial entanglement, This kind of behavior might be a natural consequence of the deep quantum connections that formed in the first moments of existence. Some scientists believe that quantum entanglement might be the missing link in reconciling quantum mechanics and general relativity, offering a way to understand how gravity behaves on quantum scales. Entanglement also plays a key role in the holographic principle theory because it connects different parts of the holographic surface, allowing information to flow between regions. If the universe began in an entangled state, this quantum information could be encoded in the fabric of space itself, influencing the behavior of matter and energy as the universe evolved. This connection between quantum entanglement and the structure of space-time could also offer insights into the nature of black holes, which are regions of space where gravity becomes so strong that nothing, not even light, can escape. Some researchers propose that black holes could act as quantum systems, with information about everything that falls into them being stored in quantum states on their surface or event horizon. In this model, entanglement would be crucial to understanding how information is preserved, even as matter is pulled into a black hole's core. This idea ties into the larger question of whether the universe itself could be described as a vast, interconnected quantum system. If the universe did begin in a state of primordial entanglement, then the connections between particles and regions of space-time may still be influencing the behavior of the cosmos today. This could help explain some of the biggest puzzles in modern cosmology, such as why the universe appears so smooth and homogeneous on large scales, despite its violent and chaotic beginnings. The idea is that quantum entanglement allowed different regions of the universe to remain connected, even as they expanded and moved apart. Efforts are also underway to explore how quantum entanglement might connect to dark energy and dark matter. Dark energy is thought to be responsible for the universe's accelerated expansion, while dark matter influences the formation of galaxies by exerting gravitational pull. Some theories propose that these unseen forces might be linked to quantum effects that arose in the early universe. If dark matter and dark energy are somehow tied to the entangled structure of space-time, understanding their behavior could help unlock the secrets of the universe's origins. The role of symmetry. Breaking in the universe's formation. Symmetry is a fundamental concept in physics, representing a state in which all aspects of a system appear identical, regardless of how you observe it. In the early universe, right after the Big Bang, it is believed that the universe existed in a state of nearly perfect symmetry. Matter and energy were distributed uniformly, and the laws of physics likely behaved the same everywhere. However, something remarkable must have occurred to break this symmetry and create the universe as we see it today, a universe filled with stars, galaxies, and a diverse range of structures. Symmetry breaking refers to a process in which a perfectly balanced uniform state gives way to a more complex, uneven structure. This phenomenon is critical in understanding how the universe evolved from an early homogeneous state into the structured cosmos we observe now. In essence, symmetry breaking allowed the universe to transition from simplicity to complexity, shaping the forces, particles, and interactions that define our physical world. In the moments after the Big Bang, the universe was an incredibly hot, dense environment. At such high energy levels, the fundamental forces of nature, gravity, electromagnetism, and the strong and weak nuclear forces, may have been unified into a single indistinguishable force. This is referred to as a symmetric state, where the forces behaved similarly and could not be differentiated. However, as the universe expanded and cooled, this symmetry began to break down, causing the forces to separate from one another. The idea of symmetry breaking comes from particle physics, where certain symmetries exist between particles and forces at high energies. As the universe cools, these symmetries break, meaning that the behavior of particles and forces changes. For example, at very high temperatures, the electromagnetic force and the weak nuclear force are thought to have been unified into a single force. But as the universe cooled, this symmetry was broken, and the electromagnetic and weak forces became distinct, taking on their separate roles in governing the behavior of particles. This symmetry breaking had profound consequences for the universe's evolution. As different forces emerged from the unified state, they gave rise to the diversity of particles and interactions that make up everything in the cosmos. The symmetry-breaking events that occurred in the early universe were not random, but followed specific physical principles that allowed for the formation of structures such as atoms, stars, and galaxies. One of the key moments of symmetry breaking in the universe's history is linked to the Higgs field, a field of energy that permeates all of space. The Higgs field is responsible for giving particles mass through a process called spontaneous symmetry breaking. In the early universe, the Higgs field existed in a high-energy state, and particles, including fundamental ones like quarks and electrons, moved freely without mass. But as the universe expanded and cooled, the Higgs field settled into a lower energy state, and particles interacting with it began to acquire mass. This process was crucial in allowing matter to clump together to form the structures we see today. It also helps explain why there is more matter than antimatter in the universe. According to theory, the Big Bang should have produced equal amounts of matter and antimatter, which would have annihilated each other, leaving behind only energy. But clearly, matter dominates the universe today. One possible explanation is that during the early stages of the universe, a slight asymmetry between matter and antimatter arose due to symmetry breaking, tipping the balance in favor of matter. This tiny imbalance allowed matter to survive and eventually form the galaxies, stars, and planets we see today. During cosmic inflation, the universe grew exponentially, stretching tiny quantum fluctuations in space into large-scale structures. These quantum fluctuations, which were minute differences in density caused by quantum mechanics, were amplified during inflation, leading to the clumping of matter that eventually formed galaxies and galaxy clusters. Inflation itself may have been driven by the breaking of a symmetry in the early universe, where the rapid expansion was triggered by a phase transition, a process similar to the breaking of symmetry in materials like magnets or superconductors. Phase transitions, in which a system changes from one state to another, often involve symmetry breaking. A familiar example of a phase transition is water freezing into ice. When water freezes, it goes from a disordered high-energy state, liquid, to a more ordered low-energy state, solid, and the symmetry of the system changes. Similarly, in the early universe, phase transitions related to symmetry breaking caused the universe to evolve from a highly symmetric, uniform state to a more structured, diverse one. These transitions set the stage for the emergence of particles, forces, and ultimately the galaxies, stars, and planets that populate the universe. Symmetry breaks are not only important for understanding the universe's early history, but also for explaining why the laws of physics behave as they do. The separation of forces, the mass of particles, and the very existence of complex structures can all be traced back to symmetry breaking in the early universe. Without these crucial transitions, the universe would likely have remained a uniform, featureless expanse, devoid of the diversity we see around us. As the universe continued to expand and cool, other symmetry breaks occurred. For example, the temperature dropped enough for protons and neutrons to combine into atomic nuclei, a process called nucleosynthesis. Later, electrons combined with nuclei to form neutral atoms, allowing light to travel freely through space and giving rise to CMB radiation. These events were all driven by symmetry breaking, as the universe transitioned from one phase to another, each time becoming more structured and diverse. While symmetry breaking helps explain many of the processes that shape the universe, it also raises new questions. What caused the symmetries to break in the first place? Are there deeper, more fundamental symmetries that remain unbroken, waiting to be discovered? Some physicists believe that there may be a deeper level of symmetry in the laws of nature, one that unites all forces and particles under a single framework. Discovering this ultimate symmetry, if it exists, would provide a deeper understanding of the universe's origins and its most fundamental laws. Higher dimensions, Could extra dimensions precede our universe? When we think of the universe, we usually imagine it in 3 dimensions of space: length, width, and height, combined with time as the 4th dimension. This understanding of space and time forms the foundation of much of modern physics. However, some theories in cosmology and physics suggest that there could be additional dimensions beyond the familiar 4. These extra dimensions could have existed before our universe began, or they may be hidden within it, influencing how the universe behaves at a fundamental level. The idea of higher dimensions is not new. As early as the 20th century, physicists were proposing theories that required more than the known dimensions of space and time. One of the first significant ideas involving extra dimensions came from the work of Theodor Kaluza and Oscar Klein, who suggested that there could be a 5th dimension. In their model, this extra dimension was compactified or curled up so small that it was invisible to us. Their theory aimed to unify gravity and electromagnetism, 2 fundamental forces, under a single framework. This was an early attempt at what would later inspire the search for a unified theory of everything. String theory, developed later in the 20th century, took the idea of extra dimensions even further. The strings in string theory can only exist in a universe with more than 4 dimensions, at least 10 in fact. In string theory, 6 of these extra dimensions are thought to be compactified, much like the 5th dimension in Kaluza-Klein theory. These extra dimensions are so small and tightly curled that we don't experience them directly in our everyday lives. The existence of extra dimensions could help explain some of the fundamental mysteries of the universe. For instance, gravity is a relatively weak force compared to the other fundamental forces, such as electromagnetism. One explanation for this weakness is that gravity may be leaking into extra dimensions, diluting its strength in our observable universe. If these extra dimensions exist, they could influence the behavior of gravity and other forces in ways we do not fully understand. Some theories suggest that extra dimensions may have played a crucial role in the formation of our universe. The early moments after the Big Bang were a time of incredible energy and density, conditions that could have allowed extra dimensions to interact with our universe in ways that are no longer possible. As the universe expanded and cooled, these extra dimensions may have become hidden, leaving only the familiar 3 dimensions of space and 1 of time visible to us. In certain models of the universe, extra dimensions are not merely a curiosity, but are central to the very structure of reality. In brain cosmology, our universe might be just one of many brains or membranes floating in a higher dimensional space. These brains could exist in a higher dimensional universe known as the bulk. In this view, our universe is a 3-dimensional brain embedded within a larger multidimensional space. Other brains, with their own universes, could be floating nearby in the bulk, possibly interacting with our universe in subtle ways. If there are higher dimensions, do they exist outside the flow of time as we experience it? Could they represent a kind of timeless reality that preceded the birth of our universe? Some physicists have suggested that the laws of physics as we know them, including time itself, may be emergent properties that arose after the Big Bang, rather than fundamental features of the cosmos. In this view, extra dimensions might be part of a pre-existing reality that shaped the conditions for the emergence of our universe. One challenge with the idea of extra dimensions is that they are, by definition, beyond our direct experience. We cannot see or measure them in the same way we can observe the 3 dimensions of space. However, there are ways that scientists are trying to detect the influence of extra dimensions. For example, experiments at the Large Hadron Collider are probing the behavior of particles at extremely high energies, where the effects of extra dimensions might become noticeable. If extra dimensions exist, they could leave subtle imprints on particle collisions, revealing their presence through deviations from expected results. Another possible way to detect extra dimensions is through their influence on gravity. If gravity is spreading into extra dimensions, it might behave differently at very small scales. Some experiments are testing whether gravity's behavior changes at distances smaller than a millimeter, where the effects of extra dimensions could become apparent. So far, these experiments have not detected any deviations from known physical laws, but the search continues. While the existence of extra dimensions remains speculative, the idea has opened up new ways of thinking about the universe's origins and structure. If extra dimensions do exist, they could offer insights into some of the deepest questions in physics, such as the nature of gravity, the unification of forces, and the origins of the universe itself. Exotic matter and the universe's origin. Exotic matter refers to types of matter that behave in ways not found in the normal matter that makes up everything we see around us: stars, planets, and ourselves. While ordinary matter consists of protons, neutrons, and electrons, exotic matter could have different properties, including negative mass, unusual interactions with gravity, or behavior that doesn't follow the known laws of physics. One of the most intriguing ideas involving exotic matter is that it might have played a key role in triggering the Big Bang, or even in the existence of the universe itself. Some scientists have proposed that certain forms of exotic matter could have been present in the early universe, creating the conditions necessary for it to expand and evolve. While no such matter has been directly observed yet, theories suggest that exotic matter might help explain why the universe exists and how it operates. One possible form of exotic matter is dark matter. While not exactly exotic in the sense of being completely foreign to our understanding, dark matter is still mysterious. It doesn't emit, absorb, or reflect light, making it invisible to telescopes. However, its presence can be inferred by observing how galaxies rotate and how gravity works on large cosmic scales. There are other, more exotic kinds of matter that might be even more fundamental to the origin of the universe. One idea suggests that there might be types of matter that existed only in the very high energy conditions of the early universe and that don't exist today. These could be particles that interacted with the fabric of space-time itself, influencing the structure of the universe as it formed. Such particles could also have strange properties, like moving faster than the speed of light, or having negative energy. Negative energy is particularly interesting in discussions about the early universe. In theoretical physics, exotic matter with negative energy could be associated with creating phenomena like wormholes, or even entire universes. Wormholes, which are theoretical tunnels through space-time, would require exotic matter to hold them open, according to current models. Similarly, negative energy could have played a role in the inflationary period of the universe, when space expanded incredibly rapidly in a tiny fraction of a second after the Big Bang. Some theories suggest that exotic matter with negative energy might have triggered this rapid expansion, allowing the universe to grow and evolve. Another type of exotic matter that scientists are investigating is known as tachyonic matter. In theory, tachyons are particles that travel faster than the speed of light, something that is forbidden for ordinary matter by Einstein's theory of relativity. However, in certain theoretical frameworks, tachyons might exist in a way that doesn't violate these rules, providing insight into the nature of time and space. Tachyons could have played a role in the early moments of the universe, influencing the way space-time unfolded. If such particles existed in the extreme conditions before or during the Big Bang, they might offer clues to the universe's beginning. Physicists are also exploring whether the Higgs boson, a particle discovered in 2012, could be tied to exotic matter that influenced the universe's origins. The Higgs boson is responsible for giving other particles mass, and it plays a key role in the standard model of particle physics. However, some theorists suggest that there could be a related particle, a heavier or more exotic version of the Higgs boson, that existed in the early universe. This exotic particle could have affected the way matter formed in those first moments, shaping the universe's evolution. Another intriguing area of research involves what is known as scalar fields, which could be considered a type of exotic matter or energy. Scalar fields are thought to be smooth, continuous fields that can exist throughout space, affecting the properties of matter and energy. Some scientists think that a scalar field might have existed in the early universe, helping to drive inflation, the rapid expansion of space that occurred right after the Big Bang. If such a field existed, it could have provided the energy necessary to kickstart the universe's formation. Exotic matter also appears in speculative theories about how the universe might have transitioned from a previous state into the one we observe today. Some of these theories suggest that, before the Big Bang, the universe might have existed in a different phase or state, governed by different rules of physics. As the universe cooled and evolved, exotic matter could have played a role in breaking the symmetry of this earlier phase, leading to the formation of the familiar matter and forces we see now. This process of symmetry breaking is a common idea in particle physics, and exotic matter could have been the key to triggering it in the early universe. The quantum foam, the landscape of pre-universe fluctuations. In quantum mechanics, the concept of quantum foam provides a fascinating glimpse into what the universe might have looked like before the Big Bang. Quantum foam, also called space-time foam, is a theoretical description of the chaotic high-energy environment at incredibly small scales. In this state, space-time itself is thought to be in constant flux, with energy and particles spontaneously appearing and disappearing at an unimaginably fast rate. Quantum foam is not something we can observe directly, but its existence is predicted by the principles of quantum mechanics and relativity when applied to the smallest possible units of space and time. Quantum foam suggests that space-time, at its most fundamental level, is far from smooth. Instead, it might resemble a constantly churning sea of activity, filled with temporary fluctuations. These fluctuations occur on the Planck scale, the smallest measurable unit, where distances are on the order of 10 to the power of -35 meters, an incredibly tiny size far beyond anything we could measure with current technology. In this foamy environment, the concepts of empty space and nothingness lose their meaning. Even in what we might perceive as a vacuum, there are fluctuations, brief blips of energy, where particles and antiparticles can momentarily exist before annihilating each other. These fluctuations are thought to be a fundamental aspect of quantum theory. One of the key ideas surrounding quantum foam is that it could be responsible for the birth of the universe. While this is still a theoretical concept, the notion suggests that our universe might have emerged from one of these high-energy fluctuations. According to some theories, if one of these fluctuations became large and stable enough, it could have triggered a process like cosmic inflation, expanding rapidly and eventually giving rise to the universe we know today. This would mean that the universe was born not from a singularity, as traditional Big Bang models suggest, but from the chaotic and bubbling sea of quantum foam. At these scales, the distinction between space, time, energy, and matter becomes blurry. Quantum mechanics and general relativity, which govern our understanding of the universe at large scales, start to break down when applied to the quantum foam. One reason for this is that quantum foam represents an environment of such intense energy density that it defies the smooth and continuous description of space-time provided by general relativity. Instead, quantum mechanics suggests that space-time itself is made up of countless fleeting events, brief, spontaneous moments where energy creates small distortions or bubbles in the fabric of reality. These bubbles in the quantum foam can have profound implications for our understanding of the universe's origins. In this high-energy state, the familiar rules of cause and effect that govern our everyday experiences might not apply. Time, as we know it, may not exist in the same way. Instead of a linear progression, time could be an emergent property that only appeared after the universe reached a certain level of stability. Before that, the chaotic energy of the quantum foam could have existed without any clear distinction between past, present, and future. Quantum fields. Could they have predated the universe? Quantum fields represent one of the most foundational concepts in modern physics, underlying everything that exists in the universe. According to quantum field theory, all particles, forces, and interactions arise from these fields, which extend throughout space. Every particle, whether it's a photon of light or an electron in an atom, is actually an excitation of a corresponding quantum field. But while these fields are typically described in relation to the universe we know today, some theories suggest that quantum fields might have existed even before the universe itself. In classical physics, fields like the electromagnetic field depend on space and time to exist. But in the quantum realm, things behave very differently. Quantum fields do not rely on the presence of particles or even the structure of space-time to exist. This opens up the possibility that these fields may have existed in some form before the Big Bang, influencing the conditions that led to the creation of the universe. One way to think about this is by looking at the concept of the quantum vacuum, a state in which particles can momentarily appear and disappear due to quantum fluctuations. Some scientists suggest that these fluctuations might have existed before the Big Bang, contributing to the sudden burst of energy that initiated the universe. If quantum fields existed before the universe, they could have been in a state of balance or symmetry. This is a common idea in particle physics, where many theories suggest that the early universe started in a highly symmetrical state that later broke down as the universe evolved. In this scenario, quantum fields might have existed in perfect harmony before the Big Bang, only to undergo a dramatic change during that event. This breakdown of symmetry could have unleashed the energy that created the universe, with particles and forces emerging from the once uniform fields. Some theories propose that quantum fields might have spontaneously generated the universe through a process known as quantum tunneling. In quantum mechanics, particles can sometimes tunnel through barriers that would be impossible to cross in classical physics. Similarly, it's possible that a quantum field could have tunneled from a pre-existing state of nothingness into a universe filled with matter and energy. This would mean that the universe emerged not from a traditional explosion, but from a subtle, quantum-level process. Thermal fluctuations. Was the universe born from heat? In the early universe, temperatures were incredibly high, and these thermal fluctuations played a significant role in shaping the cosmos. Thermal fluctuations refer to the tiny variations in temperature that occur even in seemingly uniform systems. Some scientists believe that these fluctuations could also hold clues about what happened before the Big Bang, offering a glimpse into the potential origins of the universe. In the moments immediately following the Big Bang, the universe was a hot, dense plasma. Temperatures were so extreme that particles as we know them could not exist in stable forms. Instead, energy filled space, interacting in chaotic ways. During this period, thermal fluctuations caused tiny variations in the density and temperature of this plasma. While these fluctuations might seem insignificant, they were responsible for creating the large-scale structure of the universe. The slightly denser regions eventually became the galaxies and clusters of galaxies that we observe today, while the less dense regions evolved into the vast expanses of empty space. One of the most compelling pieces of evidence for thermal fluctuations in the early universe comes from the CMB, which carries imprints of the tiny temperature differences that existed just 380,000 years after the universe began. By studying the CMB, scientists can trace these fluctuations back to their origins and gain insights into the conditions that prevailed in the early universe. While the CMB provides a snapshot of the universe long after the Big Bang, some physicists argue that thermal fluctuations might have played a role even earlier, potentially before the Big Bang itself. If the universe existed in some form of pre-Big Bang state, it is possible that these early fluctuations could have carried over and influenced the creation of the universe as we know it. One theory that connects thermal fluctuations to pre-Big Bang conditions is the idea of a bouncing universe. In this model, the universe didn't begin with a singular explosion, but instead goes through cycles of expansion and contraction. Each time the universe contracts, it reaches an extremely dense, hot state. When it bounces back into expansion, thermal fluctuations from the previous cycle could survive the collapse and carry forward into the next phase. In this way, the thermal properties of the universe could hold information from earlier cosmic cycles, offering a potential link to what might have existed before the most recent Big Bang. In addition to the bouncing universe theory, some models suggest that thermal fluctuations could arise from quantum processes that occurred in a pre-Big Bang vacuum. Quantum fluctuations might have triggered thermal fluctuations in the very early universe. If this is the case, the heat and energy that dominated the early universe may have had quantum roots, with tiny quantum events leading to the massive outpouring of energy that characterized the Big Bang. If these fluctuations existed before the Big Bang, they might have influenced the way space and time emerged. One possibility is that the early universe underwent a phase transition, much like water freezing into ice. During such a transition, thermal fluctuations could have caused certain regions of space to expand more rapidly than others, giving rise to the uneven structure of the universe that we observe today. If thermal fluctuations played a role in the universe's origins, what does that tell us about the source of this heat? Did the universe begin in a state of extreme heat, or did it transition from a cold, quantum vacuum into a hot, dense plasma? These questions are still the subject of ongoing research, but they point to the importance of thermal fluctuations in understanding the universe's early history. The limits of the Standard Model, what it can't explain about the beginning. The Standard Model of particle physics is a framework that has successfully explained much of what we observe in the universe. It describes the fundamental particles, like quarks, leptons, and bosons, and the forces that govern their interactions, such as electromagnetism and the strong and weak nuclear forces. However, while the Standard Model has been a reliable guide in understanding particle physics and the behaviors of matter at small scales, it struggles to explain certain larger and more fundamental questions, especially when it comes to the origins of the universe. One of the biggest limitations of the Standard Model is that it doesn't include gravity. Gravity, as explained by Einstein's theory of general relativity, governs the large-scale structure of the universe, influencing the motion of planets, stars, and galaxies. While the Standard Model works well for explaining the other fundamental forces, like the electromagnetic force, it simply cannot describe gravity at a quantum level. This becomes a major issue when trying to understand the extreme conditions that existed at the moment of the Big Bang, where both gravity and quantum mechanics are essential for a complete picture. The lack of a unified theory that connects quantum physics with gravity leaves a significant gap in our understanding of the universe's birth. Additionally, the Standard Model doesn't account for dark matter and dark energy. Dark matter has to be inferred through its gravitational effects on galaxies and galaxy clusters, while dark energy is responsible for the accelerating expansion of the universe. However, these entities are invisible and don't interact with ordinary matter or light in ways that the Standard Model can describe. Since dark matter and dark energy are believed to have played crucial roles in the evolution of the universe, their exclusion from the Standard Model leaves a vast portion of cosmic history unexplained. Another shortcoming of the Standard Model is its inability to address what happened before the Big Bang, or even what exactly occurred during the earliest moments of the universe. The Big Bang theory describes the rapid expansion of the universe from a hot, dense state, but it doesn't explain why this expansion happened in the first place. The Standard Model, with its focus on particle interactions, doesn't provide answers to questions about the nature of time and space before the universe began. It doesn't delve into whether there was a cause for the Big Bang, or what might have existed in a pre-Big Bang state, if such a state even existed. One of the more specific issues within the Standard Model is its handling of inflation. Inflation explains the large-scale uniformity of the cosmos, as well as the tiny fluctuations that led to the formation of galaxies. But inflation itself requires physics beyond the Standard Model to explain fully. The process of inflation is thought to be driven by a hypothetical field known as the inflaton and its associated particle. However, the inflaton does not appear in the standard model, suggesting that new physics is required to explain how the universe inflated so rapidly and what set this process into motion. Another puzzling aspect is the matter-antimatter asymmetry in the universe. According to the standard model, the Big Bang should have produced equal amounts of matter and antimatter. But as we observe the universe, it is mostly composed of matter with very little antimatter. If matter and antimatter were produced in equal quantities, they should have annihilated each other, leaving behind only energy. The fact that there is a surplus of matter is a fundamental mystery that the standard model cannot explain, indicating that there are additional forces or particles beyond the model that could account for this imbalance. The standard model also falls short when it comes to explaining the origin of masses. The discovery of the Higgs boson in 2012 provided critical insight into how particles acquire mass, but it doesn't explain why particles have the specific masses they do. While the Higgs field gives mass to fundamental particles, the reason for the particular values remains unknown. Moreover, the masses of neutrinos, which are incredibly tiny and interact weakly with other particles, are not well explained by the standard model. Neutrinos are important in the evolution of the universe, and their elusive properties might hold clues to what existed before the Big Bang. But the current framework doesn't capture the full picture. It doesn't explain how the universe's forces became distinct in the first place. It's believed that in the earliest moments after the Big Bang, the fundamental forces of nature, gravity, electromagnetism, and the strong and weak nuclear forces, were unified until the universe expanded and cooled, forcing them to split off into the distinct interactions we observe today. However, the standard model doesn't provide a mechanism for this symmetry breaking or for the unification of forces in the early universe. To explain these phenomena, physicists look to grand unified theories and other models that go beyond the standard model, yet none have been proven correct. This limitation becomes even more significant when considering the extreme conditions of the early universe. At the moment of the Big Bang, the universe was incredibly dense and hot, conditions under which the standard model's equations break down. For example, when all the forces were unified, their strengths would have been different than what we observe today. Yet, the standard model has no way of describing how the universe behaved under these extreme conditions, or how the forces separated as the universe cooled. One possible path forward is the search for a theory of quantum gravity, which would combine general relativity with quantum mechanics. String theory and loop quantum gravity are two such candidates, but neither has been fully developed or experimentally verified. These theories aim to explain what the standard model cannot: how gravity behaves on the smallest scales, and how it fits into the framework of particle physics. If successful, these theories could also provide insights into what happened before the Big Bang, offering a more complete understanding of the universe's origins. Toward a theory of everything. Can we ever know what came before? The quest for a theory of everything has long been one of the most ambitious goals in physics. This theoretical framework would aim to unify all the fundamental forces of nature, gravity, electromagnetism, and the strong and weak nuclear forces, into one cohesive explanation. It would not only describe the behavior of all matter and energy in the universe, but also provide insights into its origin, potentially offering a complete understanding of what came before the Big Bang. But this has proven to be no small task. How close are we to achieving such a theory? And is it even realistic to think that we could ever know what happened before time and space existed? One of the major challenges in creating a theory of everything is the apparent incompatibility between quantum mechanics and general relativity, which are both remarkably successful in their own realms, but don't seem to work together. The problem becomes most acute in extreme conditions, like those at the moment of the Big Bang, when both gravity and quantum forces would have been immensely powerful. Any theory of everything would need to reconcile these two perspectives, which is why physicists are searching for a new theory that goes beyond both. One candidate for this unification is string theory. However, string theory has yet to make predictions that can be experimentally tested. Without the ability to verify its predictions, some scientists remain skeptical of whether string theory is the right path to a theory of everything. Another approach comes from loop quantum gravity, a theory that seeks to quantize spacetime itself. Like string theory, however, loop quantum gravity is still a work in progress and lacks experimental verification. Even if one of these theories, or some entirely new approach,